And the next speaker will be Xiuzhen from RIKEN Center of Emergent Material Science in Tsukuba in Japan. So please, this is a 30-minute talks plus 5 minutes discussion. Thank you very much.
Okay, thank you very much. Host video. Okay, now you can see me.
Yeah, perfect.
Okay, thank you very much. So, Chairman gave me a kind introduction. I'm Xiuzhen from RIKEN Summary, Japan, and I also thank organizer gave me this precious opportunity to present our recent works on magnetic imaging for various topological spin texture listed here. And my story is quite simple and just focus how to probe this nanometric topological spin texture by using real space imaging technique. So So first of all, before my talk, I would like to thank all my collaborators, and especially for our center director, Professor Tokula, and also Professor Nagosa, and many PI, and also young research in RIKEN and the University of Tokyo involved in this research topic for the chiromagnetic material. And I'm also grateful to an international team for working on two-dimensional van der Waals magnets, and especially for Dr. Song Hong Wu in ABI, and also previously invited speaker and Professor Ferd, and also the Xizhao Zhang, and also my colleague Li Chongpeng and Femia Xin in RIKEN. So here I show you the table of contents of my talk. And first I will take a time to introduce two real space imaging methods. One is Lorentz TEM, and now it's popular, I think, in the world to probe magnetic spin texture. And the other one is we call it the differential phase contrast. And this technique is not so popular, but maybe you know this Lorentz TEM method is defocused image. And in contrast, this differential phase contrast is the in-focus imaging technique. It means it is very useful to pick up the tiny magnetic twist, such as the Néel-type skyrmion, and also other very fine magnetic structures in materials. And after this introduction for the imaging method, I will focus on the Bloch-type skyrmion and their dynamics in chiromagnets. And I also will talk real space observation of antiskyrmion and their transformation into skyrmion in chiromagnets. Finally, I will show how to identify the Néel-Bloch-type skyrmionic bubble in this two-dimensional van der Waals FGT. Yeah, I hope if I have time, I think maybe it's difficult. I will show you a little bit for the meron and anti-meron skyrmion, anti-meron square lattice. So this figure is a schematic of Lorentz TEM method. And as you know, maybe the in-plane magnetization in material actually induce a Lorentz force. And this Lorentz force perpendicular to the electron beam and also to this in-plane magnetizations. So this force also deflects this electron beam and result in the beam convergence and the divergence in the defocus image plane. And according to this principle, I mean, according to this Lorentz force deflect the electron beam, we can examine, we can probe the magnetic domain wall by using this method. And this figure is outlining the Lorentz TEM observation for magnetic skyrmion with counterclockwise and clockwise helicity skyrmion. So this white and the dark dots indicates the opposite helicity of skyrmion. It means we can use this method to determine the helicity of skyrmions. And as you know, this defocused Lorentz TEM image sometimes blurred at a big defocus volume. So to solve this problem, we also choose this in-focus phase imaging technique we call the differential phase contrast imaging at the scanning transmission electron microscopy mode. So this DPC, we call it DPC. Yeah, this DPC-STEM just use a coil to scan this convergent electron beam, and use a detector, use a segment annual all field detector to probe the phase change. And this phase, and this detector actually can scan along the four direction. It means plus minus x and plus minus x and plus minus y. It means we can directly probe this in-plane magnetic induction by using this phase imaging technique. And here I show you the Lorentz TEM observation and also DPC observation for skyrmion lattice in chiral magnets, ion germanite. And for the Lorentz TEM observation, we initially image this defocus Lorentz TEM image, under focus and over focus image. And then we use, analyze this Lorentz TEM image by using intensity of transport of intensity equation technique. Analyze this defocus Lorentz TEM image and extract the phase image. It means use this Lorentz TEM image cannot directly probe this phase image, but we can solve the transport from intensity convert to the phase image. And then once we get this phase image, we can convert this phase image to in-plane magnetic induction. Here I show you the magnetic field map for the skyrmion lattice in ion germanite. And in addition, we can, of course, we can also calculate the mx, my, and amplitude of the field. And here I show magnified magnetic field map for the skyrmion lattice. And this color wheel indicates the direction and the magnetic magnitude of the in-plane field. And this right point the field along the right direction, and this blue-green indicates the field along the left, and you can see the arrow, and it means by using this Lorentz TEM technique, combining the transport intensity equation analysis, we can also determine the skyrmion helicity and also qualitatively evaluate the field map in this skyrmion, in this topological spin texture. And this DPC technique can directly probe this MX and MY. And of course, once we get this MX and MY, we can also obtain this field map and also helicity of topological spin texture. And this performance actually was carried out for a same ion germanite sample. And you can clearly see the DPC-STEM result qualitatively agree with our Lorentz TEM observation. Yeah, here I just want to emphasize, maybe there are many arguments in the SkyMag conference this year. Many people claim the Lorentz TEM is unuseful, but here I just want to emphasize skillful to use this technique. This technique is really powerful. And in addition, other image technique is quite hard. I mean, it's just performed by using a transmission electron microscopy. It's hard to probe the dynamics of topological spin texture. Later, I will show you we use this, we skillfully use this Lorentz TEM. We succeeded in the performing the dynamics of skyrmion with electron current and also thermal current excitations. So next, let me move to the first topic, the Bloch-type skyrmion shown here, and their dynamics in chiral lattice magnets. As I think all of you know, this nonlinear spin texture induce Berry phase and also induce a fictitious field. And this field is inverse proportional to skyrmion diameter, means the smaller skyrmion size is the emergent magnetic phenomena should gigantic. I think our center director, Professor Tokla, will present some exciting electromagnetic phenomena in the chiral magnets in this Thursday. Today I skipped this in introduction for this phenomena. I focus on the real space observation. And here I show Lorentz TEM image to view twisted spin texture in skyrmion and also skyrmion lattice. And as a previous invited speaker said, this skyrmion actually promise information carrier for the future application, because this skyrmion can be driven with a small electron current. It's a several order of magnitude lower to drive the ferromagnetic domain wall. So actually, this is a first demonstration for the electron current tracks single skyrmion and the field skyrmion cluster in chiral lattice magnets. And the main contributor shown here. And we use electron, we use current pulse to probe the whole motion of this chiral skyrmion with 80 nanometer size, quite small size. So this panel, just to show you, I use this small electron current to track this single skyrmion motion in this chiral lattice magnet ion germanite. And you can clearly see this single skyrmion moved from this right upper corner to the left bottom corners with just use this small current pulse excitation. And in the left panels, actually the current flow from left side to the right side. When we reverse the current, you can see clearly reversible motion of single skyrmion from left side to the right upper side. But as you know, this current quite small, close to the critical volume for drive this skyrmion, result in a fluctuation of this whole angle of skyrmion. And here I just want to emphasize, although this fluctuation occur, but this is this in-situ Lorentz TEM observation provides the first evidence for the electron current track this single small skyrmion. So we also examine the few skyrmion cluster shown here. This is a full skyrmion cluster and accompany a single skyrmion. Here we keep the pulse current strict and just increase the pulse, increase the number of pulse. You can clearly see the single skyrmion move fast than this cluster. And interesting, in addition to this translational and whole motion of single skyrmion and the skyrmion cluster, and we also found this skyrmion cluster exhibits the internal rotational motion and indicating a torque force on these skyrmion clusters. So we also use a microsecond pulse to generate a higher order, to generate a topological object with a higher order topological charge. So here you can clearly see a skyrmion back can be generate this electron current. And we can also use nanosecond pulse current to drive this heavy skyrmion back. And we also present the skyrmion back, show the whole motion in the helix background. Yeah, very exciting to examine this skyrmion dynamics in fact. So to generate this chiral skyrmion by use a pulse current, we design a device with a notch shown here. At the initial state, you can clearly see the strip domain, and in this simulate indicate a helical state for the sample. And when we apply a normal magnetic field around 160 millitesla, we can generate a conical state. You can see the uniform contrast, monotone contrast combined by the several skyrmions. And interestingly, when we use inject the pulse current, you can clearly see the skyrmion form at the corner of this notch. And this sequential Lorentz TEM observation demonstrates this skyrmion formation around this corner of the notch with electron current pulse injections. And finally, we can see this skyrmion phase develop over the simplate and also replaced completely for non-topological conical structure. It means this electron current pulse can generate metastable skyrmions. So we also found the directional current injection effect on the phase transition in the device with a notch hole. And why this phenomena occur? Because this notch hole can induce a local spin current. And this local spin current actually converted by the inhomogeneous current distribution, and show this by this voltage and current density map. You can clearly see the inhomogeneous electron current distribute around this corner of notch. It means this local spin current is crucial to generate metastable skyrmion and then delete the metastable skyrmion. Let me explain the detail. At the initial state, we create the conical, means non-topological state, shown here, and we just inject plus current, just inject one pulse. Actually, the current direction flow from the left to the right. You can clearly see this skyrmion crystal, skyrmion lattice replace completely to replace this conical state with this skyrmion lattice. It means this plus current can trigger the phase transition from non-topological state to the skyrmion phase. And more interestingly, when we reverse the current flow direction, means from if the current flow from the right side to the left side, you can also clearly see this skyrmion lattice totally annihilated. It means this minus current can delete this metastable skyrmion. And once we apply the plus current again, you can see the skyrmion lattice recovers again. And it means we found this directional current injection effect on phase transition in this spatial device with a notch hole. So in analogy to the electron current drive chiral skyrmion in chiral magnets, we also design heater current drive skyrmion motion in the insulating magnets. And here is the main contributors, main contributors. And we choose this kappa 2 selen 03 is actually the prototype of insulating helimagnet host small skyrmion with a size of 60 nanometer in diameter. And this is a phase diagram. We just focus on the skyrmion cluster in the conical background state. And this Lorentz TEM movie can clearly show you this skyrmion move from the cold side to the hot side. Let me explain the experiment design. We put the heater at the right side and also put two thermometer at the two side of this thin plate, and we make a cold bath at the heater side and make a heat sink at the opposite side. It means we can generate the thermal current in the translational directions. So, and this Lorentz TEM image also shows that skyrmion motion in this device. First, we focus the two skyrmion island, and flow the small means heater current, just 10 micron ampere. And you can clearly see this cluster, this skyrmion island doesn't move, although the hexagonal lattice orientation changes slightly. But with increased heat current to 100 micron ampere, you can clearly see the left island starts to move towards to the right island and finally united to the skyrmion strip and moved from this cold side to the hot side. And again, for this mixed state of skyrmion cluster and conical domains, you can also clearly see this skyrmion cluster move from the cold to the right, to the hot side. And systematic Lorentz TEM observation demonstrates the main result shown here. And we plot the helicity of this skyrmion motion and marked by this right circles, and also the skyrmion hole angle marked by this triangular, blue triangular. you can clearly see both velocity and also whole angle of skyrmion increase non-linearly with increase this temperature gradient. And our experiment observation roughly agree well with our numerical simulations, and show here the velocity is not so fast, not so big, because this temperature gradient is quite small. And let me move on to the real space observation of antiskyrmion and their transformation into skyrmion, and what time I remain. Cannot check.
You have about 10 minutes.
Okay, I will go fast. Yes, so in the 2017, actually, Dr. Parkin and Professor Fields group discovered the antiskyrmion in Heusler compound. And in contrast to the isotropic DMI vector in the B20 chiral magnets, and this anisotropic DMI with the opposite sign actually favor the formation of antiskyrmion. And in our study, we use in-plane field to control this antiskyrmion in this Heusler compounds, because the in-plane field can break the symmetry of magnetic structure in our in the previous studies. So we use the in-plane field to control this antiskyrmion, and found this controlled transformation of skyrmion and antiskyrmion in this compound. Two young research in my team work on this topic. And in addition to this controlled transformation of antiskyrmion to skyrmion, and we also discovered the square lattice of antiskyrmion composed of square-shaped antiskyrmion. And this result agree well with our numerical calculations, and our simulation also demonstrates the energy state for the antiskyrmion and the non-topological bubble, and also skyrmion, in fact, it's degenerate. It means if we use this in-plane field, we can break the symmetry of the magnetic structure, and also can use this in-plane field to tune the form and also topology of this topological objects in this Heusler compounds with D2D symmetry. To calculate, to actually evaluate of a Bloch line in this antiskyrmion, actually it is a Bloch line essential to characterize the topological nature for antiskyrmion. We choose a DPC-STEM technique to quantitative characterize this Bloch line. The magnetic field map shown here, and I think due to the time limitation, I skip the explanation for this magnetic field distribution at the Bloch line. I just want to emphasize this DPC-STEM is quite useful to quantitative characterize the Néel twist in the magnetic materials. And most recently, my colleague, Dr. Karube and Dr. Taguchi discovered a new magnet with S4 symmetry. And very exciting, this material also hosts the room temperature antiskyrmion. And you can clearly see both this Lorentz TEM and the DPC-STEM observation probe, the quite perfect square antiskyrmion lattice. And we also found this periodicity of helical strips increase non-linearly with the sample thickness. And we also found this elliptic skyrmion lattice can be stabilized in very thin sample. But in contrast, this antiskyrmion lattice actually favors in the thicker samples. So let me move on the final topic as presented by previous invited speakers. And I think maybe all of you know the Néel-type skyrmion actually proposed by Professor Fert and also Professor Vincent in the 2013. And here I present some electron current to drive this Néel-type skyrmion dynamics by using electron current. I also want to skip this explanation for this work. I just want to emphasize this Néel-type skyrmion can be stabilized at room temperature. And also many work on this Néel-type skyrmion in the thin film, because this thin film is easily to fabricate a device. So recently, the Néel-type skyrmion also argued in a wonderful magnet FGT. And here, I think Professor Fert also presented this work. And research make a heterostructure of FGT and heavy metal. And they present the Néel-type skyrmion in the thin film. But the question, actually, there are many puzzles. So many work actually confirm this Néel-type skyrmion by using Lorentz TEM. But the Lorentz TEM, how can I say, cannot directly confirm, cannot directly identify this Néel-type skyrmion and Bloch-type bubble with a narrow domain wall, because both magnetic structures show no contrast at zero tilt angle. And of course, Néel-type skyrmion show contrast with a tilt angle in the Lorentz TEM. And we also, we just eager to identify the Néel-type and also Bloch-type skyrmionic bubble in this system. We choose two material. One is a heterostructure FGT with a capping layer platinum and also oxidized FGT. And other one is a pure FGT, just fabricated from the bulk sample. And you can clearly see at the zero tilt, no contrast in this heterostructure, but the bubble-like domain show in the pure FGT. It means here we can clearly we can conclude the Bloch-type bubble actually excited in this thin plate, thin pure FGT. But for this heterostructure is not clear. Although the simulation suggests the simulated Lorentz TEM image suggests the Néel-type skyrmion in this heterostructure. To escape this slide, to identify the Néel-type and the Bloch-type magnetic twist in this FGT, we use an inplane field to drive the strip domain. And first, for the heterostructure FGT, you can clearly see the inplane field align this strip to parallel to the field direction. And this experiment observation actually consistent with our simulations for the Néel twist strip domain. And in contrast, in the pure FGT, you can see this inplane field aligns this maze pattern to a strip domain, but this strip domain slant to the field direction. This is quite different to the Néel twist strip domains. So let me summarize my talk. I show you I introduced two real space imaging technique. One is the Lorentz TEM and the other is phase imaging technique, DPC. I just want to emphasize, please careful to use this Lorentz TEM and avoid the artifact. But when you probe the topological spin texture by using Lorentz TEM. And I also show you we use Lorentz TEM to demonstrate the low current drive hole motion of single skyrmion in the chiral lattice system. The proliferation and the extinction of meta-scale stable skyrmion have been demonstrated with directional electron current injections. And we also succeeded to use temperature gradient to move this 16 nanometer skyrmion in a insulator system. I also present the real space and observation of antiskyrmion and their transformation into skyrmion. And finally, I show how to identify the Néel and the Bloch-type skyrmionic bubble in two-dimensional wonderful magnet FGT. Thank you for your kind attention.
Thank you very much for this very nice and very rich talk. We are a bit running a bit out of time, but I think we have time for 2 questions. And then there will be this discussion with speaker. Everybody has received the link in the chat. So the first question from Eyong Aso, please. Can you unmute and ask?
Okay.
Thank you.
Thank you very much for the talk.
So that's the.
I have no, direct experience of Lorentz TEM, so that's why I'm asking this question. So you can extract MX, M, and Y based on your talk, but is it in a deterministic way in the sense that you don't need to have any modeling or assumption of the magnetic domain pattern, and simply looking at the intensity, can you get it, straightforwardly from an equation?
Mm-hmm. Yeah, actually, there are some noise. I cannot totally catch your question. Sorry.
Okay, so can you hear me now?
Now it's okay. I mean, previously I also heard, but there are some noise. Yeah.
Yeah. So I'm not familiar with this technique. So I wanted to know whether you can, without any modeling, just simply by straightforwardly plugging the image into an equation, can you extract MX and MY unequivocally so that no other MX and MY could give you the contrast that you get?
Okay. I think you asked the Lorentz TEM technique, right?
Yeah.
Yeah, actually the Lorentz TEM how can I say, if it doesn't use the transport of intensity equation, I mean, it doesn't use modeling, and it's hard to show the MX and the MY. For the principle, in principle, of course, MX and MY involved in this image, but how to pick up, and yeah, we need the help of this transport intensity equation. Yeah.
Okay. I guess maybe I can ask you in the private chat.
Yeah, during the coffee break. Maybe a last question from Sebastian Diaz, please unmute.
Thank you for this very nice talk with fascinating results. I have a question about what you're showing in slide 8. If you could go to slide 8, please.
Okay.
Where you have this cluster of skyrmions.
Okay.
So
yes.
Is this cluster, so is there any evidence that this is a skyrmion bag?
Oh, here I think we should distinguish the skyrmion cluster and the skyrmion bag. I mean, for the skyrmion bag, as you can see, we have a real bag, right?
Mm-hmm.
It means, yeah, but for the skyrmion cluster, actually it is open.
Oh, so
the
you
boundary,
can...
yeah, the boundary is not circular, it's open. And you can clearly see here is open.
Okay.
Yeah.
Thank you so much.
Yes, thank you.
Maybe a short related question. How do you nucleate this skyrmion bag or skyrmion cluster? I mean, do you have a specific procedure to nucleate them separately and deterministically?
Actually, I wait your question. It's quite, I should put a magic, not real magic. Actually, this skyrmion bag is hard to generate by tuning magnetic field. We use a pulse current to generate this skyrmion bag. This is an ongoing project. I doesn't totally understand the mechanism. I need a theory help. Yeah. Thank you very much.
Yeah, thank you very much. I think we have to conclude. Thank to the two speakers and to all the people in the audience. Once again, there is this coffee break and possibility to have discussion with the speakers, so you can get the link in the chat. And we come back at 12:20 for the presentation of Claudia Felser. Thank you very much.